When a gas is compressed or expanded so that no heat enters or leaves the system, the process is said to be adiabatic. Adiabatic changes of volume can be achieved by performing the process rapidly so that heat has little time to enter or leave, or by thermally insulating a system from its surroundings. A common example of a near adiabatic process is the compression and expansion of gases in the cylinders of an automobile engine. Compression and expansion occur in only a few hundredths of a second, too fast for heat energy to leave the combustion chamber. For very high compressions, like those in a diesel engine, the temperatures are high enough to ignite a fuel mixture without a spark plug, so diesel engines have no spark plugs. Here's one cycle of a 4-stroke internal combustion engine. First, a fuel-air mixture fills the cylinder as the piston moves down. Then the piston moves up and compresses the mixture, adiabatically, since no heat transfer occurs. Then the spark plug fires, ignites the mixture, and raises its temperature. Adiabatic expansion pushes the piston downward, the power stroke. Finally, the burned gases are pushed out of the exhaust valve and the cycle repeats. When a gas adiabatically expands, it does work on its surroundings and gives up internal energy, and therefore becomes colder. Blow warm air onto your hand from your wide open mouth. Now reduce the opening between your lips so the air expands as you blow. Adiabatic expansion, the air is cooled. Air temperature may be changed by adding or subtracting heat, by changing the pressure of the air, or by both. In the atmosphere, heat can be added by solar radiation, by long-wave Earth radiation, by condensation, or by contact with the warm ground. Heat may be subtracted by radiation to space, by evaporation of rain falling through dry air, or by contact with cold surfaces. For many atmospheric processes, the amount of heat added or subtracted is small enough that the process is nearly adiabatic. In this case, an increase in pressure will cause an increase in temperature and vice versa. We then have the adiabatic form of the first law. Change in air temperature is proportional to pressure change. Adiabatic processes in the atmosphere occur in large masses of air that have dimensions on the order of kilometers. We'll call these large masses of air blobs. As a blob of air flows up the side of a mountain, its pressure lessens, allowing it to expand and cool. The temperature of a blob of dry air that expands adiabatically changes by about 10 degrees Celsius for each kilometer of elevation. Air flowing over tall mountains or rising in thunderstorms or cyclones may change elevation by several kilometers. Air at 25 degrees Celsius at ground level would be minus 35 degrees Celsius at 6 kilometers. If air at negative 20 Celsius at an altitude of 6 kilometers descended to the ground, its temperature would be a roasting 40 degrees Celsius. An example of this adiabatic warming is the Chinook, a warm, dry wind that blows from the Rocky Mountains across the Great Plains. Cold air moving down the slopes of the mountains is compressed into a smaller volume and is appreciably warmed. Communities in the paths of Chinooks experience relatively warm weather in midwinter. A thunderhead is a result of the rapid adiabatic cooling of a rising mass of moist air. Its energy comes from condensation and freezing of water vapor. If a hot brick is next to a cold brick, heat flows from the hot brick to the cold brick until both bricks arrive at thermal equilibrium. If the hot brick takes heat from the cold brick and becomes hotter, the first law of thermodynamics is not violated. However, this would violate the second law of thermodynamics. The second law of thermodynamics describes the direction of heat flow in natural processes. Heat flows one way, from hot to cold. In winter, heat flows from inside a warm heated home to the cold air outside. In summer, heat flows from the hot air outside into the home's cooler interior. Heat can be made to flow the other way, but only by imposing external effort, as occurs with heat pumps. There's a huge amount of internal energy in the ocean. All this energy can't be used to light a single flashlight lamp without external effort. Energy will not of itself flow from the lower temperature ocean to the higher temperature lamp filament. There is also a third law of thermodynamics. No system can reach absolute zero. As investigators attempt to reach this lowest temperature, it becomes more difficult to get closer to it. Physicists have been able to record temperatures that are less than 1/millionth of 1 Kelvin, but never as low as 0 Kelvin.